Hey everybody. Today we're going to do an example of how to use Descartes' Rule of Signs to determine the number of positive and negative real zeros of a polynomial. It's a pretty complicated theorem, and there's a lot going on in this section, but how do we actually use it? It actually isn't that hard to do. So let me just read it to you, and then we'll do an example, and you can see why it's not too hard of a thing to implement. So the theorem is called Descartes' Rule of Signs. It says, let f of x be an n-degree polynomial with real coefficients given by a sub n minus 1, all the way down to a sub 1 and a sub 0. Okay, so those are all numbers. They could be 0, some of them, but they're all real numbers. Okay, the number of positive real zeros, so that means the number of possible roots of this equation. So if I put 0 equals f of x, there's just some solutions there that might be real numbers. The number of ones that are on to the right of the y-axis is equal to the number of sign changes among these coefficients, or that number minus some even number. So if, for example, n were 5 and there were 5 sign changes, then I could have all 5 of the zeros be real positive real zeros, or 3 or 1, because 5 minus 2 is 3, 3 minus 2 is 1, right? So if there are 4 sign changes among these guys, then I could have 4, 2, or 0. Then you do the same thing when you plug in negative x. So that's going to change, right? What happens when you simplify that function, f of negative x. Okay, basically it's this thing, but then we're gonna flip it about the y-axis and do the same. Use this same first assertion. Okay, so here's an example we're going to do. So determine the number of positive and negative real zeros that are possible. Okay, for each of these. So let's look at this here. So if we see the number of sign changes of f of x, notice that the degree is 8. So there's possibly 8 real zeros of this. Okay, but not necessarily. Okay, there could be some, and that's with multiplicity. There could be some that are imaginary or complex, right? So fundamental theorem of algebra says that there are exactly 8 complex zeros of this polynomial, but not all of those might be real. But Descartes' rule of signs is really simple. So if I look at negative 2x to the 8th minus x to the 5th plus 4x cubed plus 6x squared plus 18x, notice that I'm going to go ahead and write this in descending order, and that's, you need it written in that way, or this doesn't make any sense. So if I look at the sign changes, so here it starts out being negative, stays negative. There's no sign change there. Here's 1, right? It goes from -1 coefficient to 4. That's a sign change. Okay, then we're at positive, still positive, still positive, and then we change from positive 18 to -4. So there are 2 sign changes. So 2 sign changes. Means that there are 2 or 0 positive real roots or zeros possible. Okay, it doesn't tell you what they are, it just says how many you might have. Okay, on the other hand, if we do f of negative x, okay, notice if I plug in negative x in for x everywhere, right, with a parentheses, where you have an even power, it doesn't change the coefficient, okay? So, but where you have an odd power, so note, negative 8 all raised to the 8th power is still positive x to the 8th. So it didn't change the coefficient there. It's going to do that here, right? Negative x to the 5th is negative x to the 5th. So negative x, the quantity to the 5th, is equal to, indeed, negative x to the 5th, right? So these are going to cancel. So actually, when we do this simplification, this becomes now a positive. That's going to be negative, because that's to the 3rd. That's the 2nd, so it doesn't change the coefficient. That's to the 1st, so that will. Okay, so just got to be careful, because transcription errors will definitely screw you up here. Okay, what we got? So we got a sign change here from -2 to +1, then another sign change from +1 to -4, another sign change -4 to +6, another sign change to -18, and then not there. So 1, 2, 3, 4. There are 4 sign changes there. So we have 2 or 0 positive real roots. We could have up to 4 negative real roots. And if we look at this one here, okay, I'm going to do this sort of quickly now that we've seen it done once. So let's see. If I do f of x here, I get 1, 2 sign changes. Okay, so that's going to tell me in part B here, once again, we have 2 or 0 positive real roots. Okay, and if I look at what happens when I put f of negative x in there, what happens? So if I put negative in here, this becomes negative, this stays the same, this stays the same, this becomes negative, and that stays the same. So if I look at my roots here, so negative, negative doesn't change, negative, negative. Oh, that's one sign. There's only one sign change when I do f of negative x. Okay, so 1 negative real root is the only possibility, right? So here, this is kind of interesting. We have 1 negative real root. There's only one, right? If this had been 3, I could have 3 or 1. Okay, 5, I could have 5, 3, or 1. Here, if it's exactly 1, right, there's no ambiguity here. That's the only case. Okay, so I hope that helps with you guys doing these problems. And I will see you on the flip side.